Namaskar, everyone. I'm Rohit Karnik, and it's indeed an honor to be invited to be part of the 125th year celebration of the CKP Education Society. So, today I have some questions that the society has asked me that I will answer with the goal of sharing some of my experience and my journey. So, first question is, can you explain your academic history? So basically, I'm from Pune, and I did my schooling all the way to junior college in modern high school and Vidya Bhavan school. And then after that, I went to IIT Powai. So there I did my BTech in mechanical engineering. And um, I was doing fracture mechanics for my undergraduate thesis. Then I went to Berkeley, UC Berkeley in the San Francisco Bay Area. There I did my master's and PhD in mechanical engineering department, but focusing more on the field of nanotechnology. And after that, I went to MIT. I got a faculty position, but I postponed it by 1 year, did a postdoctoral training in chemical engineering and then joined the faculty in mechanical engineering at MIT in 2007, and I'm still there. So in academia, apart from just the professor's role, I've also done some administrative roles, such as being the undergraduate officer or associate department head. And currently, I serve as associate director of Water and Food Systems Lab at MIT, which is a center that distributes funding, and also a faculty director of a school-wide interdepartmental engineering education program. So next question is, what made you go for engineering and then post-graduation and doctorate in nanotechnology? So if I think about my career and my trajectory. So when I was a child, I always liked to play around with things. So I would do things like observe what ants are doing, what happens if you take ants from one ant colony, put it somewhere else, or what happens if you take a lens, playing around with lenses. Then my parents got me a small telescope when I was, I think, around 10 years old. So I enjoyed watching the stars. I used to like to go up to my terrace of the house and then just see what's around. So I enjoyed nature and I also wanted to explore. Then I started to build things. And I had an inclination towards astronomy. So I went to Pune University's Inter-University Center for Astronomy and Astrophysics, made telescopes, so making mirrors by my own hands. And then I started thinking about career. So there, the trade-off between practicality and reality. So going to engineering and taking the opportunities from there seemed to be much more attractive. So that allowed me to combine this urge to explore, but also this inclination to make things and play around with things. And I got inspired by my mama, Mukund Konvikar, who used to make special purpose machines, and I had visited his factories. And so that was very fascinating. So on one hand, I had this urge to explore and understand things, and on the other hand, this inspiration that you can actually use that knowledge to make something useful. And so I decided to go into mechanical engineering because it's a very broad and versatile field. So I did my bachelor's there. And then for my fourth year BTech project, I was working on fracture mechanics, and it was interesting. But this urge to really explore and understand more broadly what is happening in the world was there. So then I read this book on nanotechnology called Engines of Creation, and it talks about little machines making small molecularly precise things. So it was a little bit of a controversial book at that time in terms of its claims being too tall, but it sparked this curiosity and inspiration. So then I started looking at graduate school. What are the different programs? And I found a really good match at Berkeley with Professor Arun Mazumdar, who was doing nanoscale and microscale technology. Then I decided to go there. So I went to Berkeley and did my master's and PhD in micro and nanoscale technologies. So as I think about it, also nanotechnology is a very vague word. So if you think about uh, what is nanotechnology, it's really about doing things at the small scale, at the nanometer scale. So our hair, um, it's about 100 microns or zero point 0.1 millimeters. And micron, you go 1,000 times lower, 100 nanometers. So those are the length scales we are talking about. And there have been tools that have developed that allowed us over the past 50 years or so to really start looking at those length scales and manipulating them. And that is what the field is. So it's a very broad field. And in that broad field, my focus was fluidics, so micro and nano fluidics, which deals with how do fluids or ions, molecules, cells, how do they flow at these small length scales, and how can we make devices or materials to control them. So the next question is, what are your different projects going on in nanotechnology, and how do you find them useful in our normal life? So after coming to MIT, I started my own research lab called Microfluidics and Nanofluidics Research Lab. And we have worked on a lot of different projects, ranging from applications in biotechnology to sensors to filtrations and membranes. So some examples are like water filters or making membranes that are really trying to push the field, developing new concepts, and sensing things for water quality or for diagnostics. So what I'll do is I'll share a little bit of my background, and I'm going to share my screen now. Okay, so I hope my screen is visible. So uh, these are some slides. So these are from the early days that I talked about. I was interested in making telescopes. So what you see here is me looking through the telescope, and you can see the 6-inch mirror that I made by my own hands. This is a photo from uh, uh, um, IIT, and we are basically part of this ASME competition. And so we are making a machine that can fill um, fill a bottle with water or a fluid and then cap it. This is from Berkeley. So basically, what you see up here is me in the microfabrication lab. So it's a clean room, so very low level of particulates, and then we have to wear this suit to prevent skin flakes or hair or other things from creating dust. And so there are different machines there that you can use to really fabricate and examine things at the small scale. And then the photo that you see is my advisor, PhD advisor, Professor Majumdar. And this photo to the side is this tower called Campanile, which is a iconic tower at Berkeley. This is my group and some of the pictures at MIT. So MIT campus is located close to Boston. So in the picture here of the building, you can see Boston in the background, and that's a photo of me in the lab. And this is a photo of my group from about a year ago. So let me talk a little bit about some of the research work. So this is a project that I started when I was a postdoc and continued for several years as a professor. So the concept was, how can we analyze cells? So cells, as you know, are important for for really keeping us alive, and they are critical in building blocks of all biology. And so the idea is now these cells have different molecules on the surface that help us to analyze the cells, or the cells can then, different types of cells have different molecules on the surface, so we can distinguish cells that way. And the concept that we explored was, what if we can flow cells over surfaces that have molecules that can then grab onto the cells, but instead of sticking, they will move the cells, so that they can um, basically be sorted and analyzed. So we built devices like the one you see here. And then we were also able to make these devices where these black lines are lines, very thin lines of molecular patterns. And you can see the cells coming out at an angle from whole blood. So you can basically take a drop of blood and isolate the white blood cells called neutrophils and analyze them in a relatively simple manner. So that was an example of a project that relates to diagnostics. And this kind of technology might be helpful to basically quickly assess inflammation and inflammatory related diseases, as well as really emergency diseases like sepsis. The second snippet I'll talk about relates to um, more industrial scale separations. So this is a photograph of an oil refinery, and these buildings that you see, these tall buildings like tubes, they are distillation columns. And they can do a lot of different kinds of separations, ranging from separations related to manufacturing of many of our chemicals and plastics, to separation of solvents and other materials. And they really account for about half of the US industrial energy consumption. So this chart on this pie chart here shows in green the US industrial energy consumption, and about half of that is because of separation processes, and about 90% of that could potentially be saved if we can move to dramatically more efficient technologies. So if we think about the future, we have to reduce carbon emissions and make things more efficient and sustainable and recycle more. So we have to go to low energy or more efficient separation processes. And so instead of distillation, which is at the high end of the energy consumption spectrum, can we go to membranes, which are at the lower end? So that's the motivation for one of the major projects in our lab. So the idea that we have is, can we make the ultimate membranes just one atom thick? And if we can make holes in the membranes, as you can see here, then we can use it for separations. And these membranes are extremely thin so that they can provide very compact and low energy consumption separations. They can withstand high pressure because they are strong, and that might allow us to have high material efficiency, so higher recoveries of materials, and they're chemical resistant. So they can perform in different kinds of fluids, which are challenging for most membranes. So what you see here is an actual photograph of a membrane from our lab, and it's about this big. And if you zoom in, these are actual atoms that you can see. And the red arrows point to holes that we have made in the membrane. So this membrane is about 20 nanometer by 20 nanometer. So it's about 10 centimeters on my screen. And if this is the level of zoom, the actual membrane will be 50 kilometers. So that is the scale we are looking at. So we have the technology to be able to make these holes at the few atom scale. So we have developed different kinds of technologies related to it. So how do we make these atom scale holes in the membrane? And we do it by irradiating ions onto the membrane, and we can see these pores emerge. We have also looked at how do we make them robust and defect tolerant. So you can assemble molecules and do modifications to make them robust. And we can also look at how to design the entire membrane. So this one atom thick layer sits on some support. How do you design that? What are the principles and so on? So we are looking at different applications as well, apart from the fundamental technology. So we are basically looking at water filtration. Can we do water filtration more effectively or remove contaminants that are difficult to remove? Ion-ion separation. So for example, can we separate lithium from other ions, and these might find use in battery recycling or improved efficiency in mining or e-waste recycling. We are looking at gas separation, like hydrogen separation at high temperature, and then various separations in chemical manufacturing related applications. So in this plot that I've shown, there's two molecules. One of them is linear, one of them is branched. And what you're seeing is basically the flow rate through the membrane normalized by some factors. And it really starts to drop off as the molecular cross-section, which is on the x-axis, increases. So the membranes can distinguish between molecules that are, let's say, 0.55 nanometer versus 0.6 or 0.65 nanometers. We have applied this to high temperature hydrogen separation, which is important in industrial processes like dehydrogenation reactions or for hydrogen storage using liquid oxygen hydrogen carriers. And this data are at 500 Kelvin, so about 200 degrees Celsius, where it's very difficult for most membranes to operate. And we were able to show that these membranes can do this separation for prolonged periods of time. So one of the membranes we basically kept at this temperature for over a month, and it was stable. On the bottom, you see measurements with different kinds of solvents and the membrane showing stable performance over hundreds of hours. And then on the other corner, you can see the three different kinds of molecules. The linear one goes through, and the other two are filtered out in a pressure-driven filtration process. The next example is actually related to water filtration. And in this photograph, you can see me. This is by the Dead Sea in Israel. And it was a conference organized by NATO that brought together like engineers like me, then people who are doing things like studying what is the mechanism of erosion of Angkor Wat by pat urine. So urine goes in crystals form and then the rocks crumble, that kind of thing. And then people looking at flow of fluids in plants. So we have all seen in high school or school that plants take water from the roots and it goes up and then evaporates from the leaves. And if we look at the structures responsible for it, there are these really fine structures. And if you zoom in at the micron scale, there are membranes there. So we asked the question, can we actually use these for water filtration? And if we could, these are naturally available. You can source it from the waste product of the lumber industry, which is often just converted into mulch or pulp or discarded. And then it would provide more sustainable, lower cost, scalable and agile water filtration devices. So we were able to show that which trees to select, we can select, and how we can make these filters. And you can see in these microscopy images that we were able to show that bacteria get trapped in it. And we did quite a bit of work on understanding how this material, this tissue that conducts this fluid in plants called the xylem tissue, how it can be engineered as a water filter. So we also did work in Uttarakhand. So you can see a photo from there. With natural spring waters, we were able to show that the filters can provide comprehensive protection as per WHO guidelines using real bacteria contaminated spring waters. So there's been quite a bit of student and public interest in this project because of its this nature can be used directly for filtration. So you can see some of my students. So an early student, high school visiting at MIT, she won a prize at the Intel Science Festival. Another of my students, you can see doing a demonstration in a museum affiliated event in Bangalore. And then we also have a website on xylem water filters to provide information for those who might want to do science experiments. And this is a quote from a teacher, and I will read it out. I was the coach of the 4 kids, including Shrey, who were working on the xylem filter for the first Lego League competition. We are very happy to tell you that our project was very well received yesterday and have been invited to the next stage, innovation competition. This project has inspired the kids on how to research issues, understand that billions lack basic necessities such as clean water, and they can put their brains together to address these issues. So it was very rewarding to see the impact on students like this. And we have continued to advance this technology. So you can see my student Kritika here in Delhi demonstrating the filter and getting feedback. And then we are also trying to commercialize this for agile water distribution in humanitarian aid, disaster relief kind of applications, and other uses. So you can see the water can get filtered quite nicely through these filters. Going on to the next question, how do you look at the future of nanotechnology? So there is several trends that are going on, and nanotechnology itself, as I mentioned, it spans a lot of different fields. So one analog is, let's say, we can manipulate things at the millimeter scale. Let's say we can do machining or make features at the millimeter scale. Then we might say, okay, millimeter scale or millimeter technology or milli technology. So you can imagine that could involve everything from screwdrivers and screws to light bulbs to a bunch of other things, to cloth, everything. So nanotechnology is not very different from that. There is a lot of different subdomains. So it's of course only possible to predict the future after it has happened, right? So it's like difficult to say what the future might be. But there are some trends that will that have momentum, and they will end up influencing where we go in the future. So one is clearly climate change and the associated challenges, and that is one of the defining challenges of this century. So if we think about climate change, we need to have more sustainability. So technologies like batteries, they have a lot of features at the nanoscale, improved chemical manufacturing, catalysis, more thermal energy storage and materials to do that, hydrogen-related technologies, then chemical and industrial separations, and how do you improve the efficiency? How do you recycle? All of these, nanotechnology has a role to play. The other trend is the chips in AI, right? So if you think about the computer, the chips that are there, they have nanoscale features that are controlled. And as AI and computing become more and more advanced and more demanding, there will be quite a bit of advances needed to fuel that. So a lot of researchers are looking at how do you make more efficient chips, because in the future, maybe most of the energy consumption of our civilization or human civilization is going to be for computing. Then looking even further, so nanomaterials and nanomaterial-based composites, those will slowly start to come into daily life. So advanced composites that take especially carbon-based feedstocks and make them into advanced composites that can be lighter and stronger for applications in aircraft, cars, and others. Then more improved industrial processes. So for example, improved water treatment, then improved separations and so on. Then quantum computing, I think that will also require a lot of nanotechnology-based advances to make it happen. biotechnology will have a big footprint there. And this is very broad. So it can range from something like drug delivery or vaccines. So if you look at the Moderna and Pfizer vaccines, they are based on nanoparticles. And these are engineered particles designed to carry the RNA into the cells. So biotechnology will actually start to evolve where you can actually tailor and program things into biology and control things at the nanoscale. Because today in biology, proteins are molecularly or atomically precise. Plants or human body can make proteins that are a particular structure, and they can make it reproducibly, and they can make it at scale. So as biotechnology progresses, we will have more and more control over how different biological systems can do something that might be useful. So for example, maybe you can have living sensors, or you could have um, plants that might perform certain sensing functions, or bacteria or yeast that might produce some chemicals that we need, and so on. And then the interface between human and computer, so brain interfaces, those are also micro to nanoscale interfaces, and those will, I think, will continue to grow. And perhaps in 100 or 200 years, there will be brain-computer interfaces for pretty much all people. Now, that is quite a possibility. And in AI, you have seen this ChatGPT was launched. There's like a huge instantaneous kind of jump. Nanotechnology, I think, is a little bit different because it's slowly percolating, and it will continue to percolate. So, for example, Moderna and Pfizer vaccines, they are really based on nanotechnology, and they wouldn't be possible if we didn't have control over the nanoscale. Then the chips in our computers, so these are getting smaller and smaller. The features are in the few nanometer length scales now, but we don't really think about it as nanotechnology. Then different diagnostics are there. They use micro to nanoscale technologies, but they are not in the public consciousness as such. So I think nanotechnology is very cross-cutting, and it will continue to influence and advance and percolate everywhere. So next question is, what efforts should students take to get into this field? So again, it's a very broad field, and so uh, uh, I would say it's solidly based in science and engineering. So have to be good at science and mathematics. So of course, like interest in science and mathematics, and you have physics, chemistry, biology. Nanotechnology spans all of them. So if you're very interested in physics, there is room for you in doing something in nanotechnology. So maybe it might be nanoscale optics or photonics. In chemistry, you can do different kinds of syntheses, or make new kinds of materials with control over the nanoscale. In biology, you can engineer cells or molecules. And so in terms of preparation, I would say interest in science and math and really understanding the fundamentals. And what aptitudes can you pinpoint if somebody has to enter this field? So it's a very cross-cutting, interdisciplinary kind of a field. So interest and passion and dedication to science and engineering is absolutely key. Curiosity. There's a lot of different dots that can be connected. So being curious to learn, and then the ability to think both broad and also deep in at least one or two areas. The ability to learn independently. So rather than somebody teaching, can we go and learn something new? And then can we connect different pieces, different disciplines, and think creatively? And these aptitudes are things that we can actually cultivate within ourselves. Then next question is, what are job or business opportunities in this field? So again, it varies a lot, and there are a lot of different opportunities. So these include academia, of course, and then research in industry or government labs. A lot of students who work in nanotechnology end up being entrepreneurs and start new companies that are based on the technologies they develop. Then these might include things like advanced batteries or membranes or composites or sensors and so on. Then you have the big technology-based companies like Intel, Apple, Applied Materials, and so on, medical device companies, pharma and biotech like Moderna or Pfizer, and then a lot of industries based on materials and chemistry, including like battery manufacturing and recycling, cosmetics, coatings, and so on. So it's really very cross-cutting. Then my advice to students. So as you think about what is it that you're going to do in your life, a large part of your life is going to be devoted to your career. That's the norm. It might change in the future, and it may not be true for everyone. But the norm is a large fraction of your life is going to go into the career. And so the question is, what is it that is worth that chunk of your life? What is it that you're so interested in, so passionate about, and so convicted? You have this conviction that this is what I want to do and this will make my life well spent. So you need to have this real inner passion and sense of mission. Because if you're doing something for somebody else, to please somebody else, that's going to be a very heavy price to pay with that much amount of your time. So what is it that's going to make your time and energy well worth it? So identifying this mission you're calling. And sometimes you may not know, but don't cease searching for it. Then being open to opportunities, you never know what opportunities will come. And take chances, but don't be reckless or rash. If you don't take chances, if you don't challenge yourself and put yourself in situations that make you uncomfortable, you will not make progress, you will not learn new things. So there's this balance. Take the opportunity, take chances, make yourself uncomfortable, but do it without being reckless or rash. Then know that you can actually develop your own thinking. So it's not like somebody is, like this person is so good at thinking in this way, I can never do that. You can observe and you can learn and strive to actually change your thinking, and that is possible. Observing and connecting the dots. So rather than gathering information, it's more about seeing the higher picture and the connections. So as you learn and observe things, see how things connect that might otherwise seem to be unrelated. Then our world is changing. So there's climate change, there's AI, there's other things going on. And so being adaptable is very important. And then God has given us this life. So it is our responsibility to use it for our own advancement and for the advancement and betterment of the world. So, if you ask yourself the question, what can I do that will make the world a better place? And that is the question you should be asking every day. And I also strive to live my life in that way by asking, what is it that I can do that will make the world a better place? And that goes from thinking about big picture to how you interact with the people around you. How do you inspire people? Are you kind to people? Are you being selfish, or are you really thinking about the bigger picture? Then the last point, which is actually very important, is India has a very rich spiritual heritage. So be curious to learn about it. Find out what the Gita says. And not just intellectually, but learn to live it. And as you go outside into the world, also go within and strike that balance. And that is the key to a really fulfilling life. So I think I have probably exceeded my time. So I'm going to end here. Again, thank you for listening. And it was an honor to be invited for